this is your video for 6.5, the trapezoidal rule, and this is actually our last section in chapter 6 where we're talking about integrals and some ways to evaluate them. So your trapezoid is going to be a much more effective way at approximating area than using a rectangle, because when you have curves, rather than putting a flat top on the top of those, it makes more sense to make kind of a slant or a little secant line, which is what you have whenever you have these trapezoids. So the bottom is still going to be flat, and then you have your vertical sides, but then your top is going to be slanted. And that's why we have the formulas here that we do for trapezoids rather than for rectangles. So the formula for area of a trapezoid, in case you did not know that, it's 1/2 base 1 plus base 2, and then times the height. So that's where the h's in all of these, that's going to be your height. The divided by 2, that's the 1/2. And then on top, you have your y0 plus y1, y1 plus y2. You have y2 plus y3. So your y's are going to be the different heights because you have your two bases that make up your trapezoids. The first and last values, so the y sub 0 and the y sub n, those ones are only used once because they are only attached to one trapezoid. But all the ones in the middle are actually going to appear in two different trapezoids. So here is your official trapezoidal rule. It's going to be h over 2 because they were all divided by 2 and they all were multiplied by h. I can actually pull out that h over 2, and then I would add up the lengths or the heights in between of the different trapezoids. So again, the y sub 0 appears once, the y sub 1 appears twice, y2 is twice, y3 is twice, and so on and so forth until you get up to yn, which again only appears once. To figure out your h, you have to figure out how many subintervals you're partitioning your area into, and then you have to do your b minus a. So b minus a over n is going to give you your h if they don't come out and tell you what your h is. And the interesting thing about the trapezoidal rule is it is actually the average of your LRAM and your RRAM for whatever n you decide to have. One of the questions in your homework, I believe, does ask you to prove this. So you would write out your LRAMs, write out your RRAMs, do the divide by 2, and you'll see that it ends up being the exact same formula as the trapezoidal rule. So example 1, we're going to use the trapezoidal rule. It says n is equal to 4 to estimate the integral below, and then compare the estimates with the value of fn, so that's using the calculator, and with the exact value. So, if n is equal to 4, I have, and again this is using the trapezoidal rule, it's b minus a over n, so 2 minus 1 over 4, and then that whole thing divided by 2 of, and then I have to do my values. So I have my y0, which is actually going to be y1, 2 times my next interval, and again, I'm splitting this into 4 pieces, so that's 2 times y of, and I'm actually going to get rid of that second thing there, 2 times y of 1.25 plus 2 times y of, and I did it again, don't need that in there. 2 times y of 1.5 plus 2 times y of 1.75 plus y of 2. So again, if I'm going from 1 to 2 and I'm splitting it up into 4 different trapezoids, the first one is going to be the 1 and 1.25. Second one is 1.25 and 1.5. Third one is 1.5 and 1.75, and the fourth one is 1.75 and 2. So y of 1, plug in 1 into the function, I'm going to get back 1. The second one, plugging in 1.25 into the function, 1.25 is the same thing as 5/4. That might be a little bit easier to work with because I am squaring it. So 5/4 squared is 25 over 16. 3/2 squared is 9/4. 7/4 squared is 49 over 16, and then 2 squared on its own is simply 4. So 2 minus 1 is 1. So 1/4 divided by 2 is going to be an 8 times everything that we have up here. So that's 1 plus, I guess I'm not going to make that 50 over 16. I can reduce that a little bit. That is going to be 25 over 8 plus 9 over 2 plus 49 over 8 plus 4. And that is going to equal 75 over 32, which is 2.34375. So if we compare that to the actual integral value, the actual integral from 1 to 2 of x squared dx is 7/3, which is 2.3 repeating. If we do the Fn int, that is equal to 2.33333. So again, you get the idea that the decimal is repeating even though it's not exact like it is for the integral value, but all of those are very, very close together. Your book actually goes through the percent error for this, and the percent error is actually 0.4%. So this is, even just with 4 intervals, that's not a very high end. This gives us a really, really great approximation of the actual value. One thing to know about the trapezoid rule is that it will overestimate if your graph is concave up. That's because the top slant of your trapezoid is going to be above where the curve is, and it's going to underestimate where the graph is concave down, because again, that slant is going to be below the curve. I'm actually going to skip example 2. This is covered in your textbook, and there's a chart in your textbook that you need to read in order to get those values. I believe your book video covers this as well, so I'm going to skip this for right now. And that brings us to Simpson's rule. Simpson's rule is the last rule that we are going to look at in this class for evaluating functions without actually going through and finding the integral. Typically, Simpson's rule does not appear on the AP exam, although I feel like I did see an exam question recently where it did show up, so it is important that you do know how to use it. This is very similar to the trapezoidal rule, only instead of your h over 2, you have h over 3. And this one has the caveat that you have to partition into an even number of subintervals. So if you were dividing into 5 pieces, you couldn't use Simpson's rule. If you're dividing into 15 pieces, 17 pieces, you can't use Simpson's rule. And that's because of the rotating between the 4s and the 2s. Simpson's rule uses curved pieces instead of trapezoids to get those approximations. The formula is very similar, but instead of after the y sub 0 for the y1, instead of starting at 2, it actually starts at 4. So it's going to rotate back and forth between 4s and 2s until you get to a 4 and then back to a 1 again. And h is found the same way that it was for trapezoidal rule. So we're going to do Simpson's rule on this, and we are going to use n equals 4 to approximate our value here. So our Simpson's rule is going to equal h over 3 times our y sub 0 plus 4y1 plus 2y2 plus 4y3 plus y4. Well, I'm starting at 0. So my y0, that's actually going to be f of 0. Now I'm dividing from 0 to 2, I'm dividing that up into 4 different pieces. So each piece is going to be 1/2 long. So next is going to be f of 1/2, and then 1, and then 3/2, and then 2. So whenever I'm plugging in and evaluating, that's what I'm actually going to get. So h is 1/2. 1/2 divided by 3 gives me a 6. Now I plug in my values. I plug in 0, I'm going to get 0. I plug in 1/2, notice I am multiplying that by 4. Plug in 1/2, 1/2 to the 4th power is 1/16, times 5 is 5/16. Next one I multiply by 2. When I plug in 1, I'm going to get 5. Then I multiply by 4. When I plug in 3/2, 3/2 to the 4th is 81 over 16, and then times 5 is 405 divided by 16. And then I plug in the 2. 2 to the 4th power is 16, times 5 is 80. So when you go through and do this, you end up with 385 over 12. You can use that. This actually approximates to 32.083 repeating. And if you find the actual value is 32, so this error is actually 0.26. So this does give us a really great approximation of the area underneath the curve. There is an error analysis in your textbook on page 314 that goes through finding some of the errors and talking about the errors and the different methods. So that is something you can take a look at as well. So that's going to conclude the 6.5 video. This one wasn't as long as some of the others from this section, or from this chapter. So go back through, rewatch the video. There are some videos from Khan Academy videos on the trapezoidal rule that are in a folder for your class. So you can watch those as well. And reach out to me if you have any questions.